Hey guys, today we are going to discuss another problem, which is tree tag. It's also a 1900 problem. So, as always, we are going to start with the example here. So, there are going to be 4 test case, and for each test case, it will give us 5 numbers. The first number is the number of nodes in the graph, right? We have 4 nodes in the graph. And the second is the starting point of Alice, which is 3, right? The red node. And the third number is the starting point of Bob, which is this node. And this is the maximal number of step can be made by Alice, which is dA, right? The distance A can make for each step, right? And this is dB. So the following lines are the edges: 1, 2, 1, 2, 1, 3, 1, 3, and 1, 4, 1, 4, right? And essentially, Alice is going to chase Bob, and the number of Alice number of steps Alice can take is 1, right? So in each round, Alice will move first, and she can take 1 step here, and Bob can move 2 steps at a maximum, and um, only the starting point and the ending point counts. So if Alice stands here and Bob moves from here to here, they don't encounter each other, right? Only if Bob stays here or anywhere and Alice move to that location and they occupies the same node, at that time we call Alice wins, right? So there are infinite number of rounds. So our job is to decide um, whether Alice or Bob can win the game, right? So for the first example here, because Alice is here and Bob is here, so the first in the first round, Alice can move here, right? And Bob can move here, stay here, move here, or move here, right? No matter where Bob decides to move, Alice can always move to that location in the next round, right? So Alice will always catch Bob. So we output um, Alice here because Alice wins, right? And for the second test case, so we have 6 nodes, and this is Alice's starting point, and this is Bob's starting point. And in each round, Alice can move 1 step, right? And Bob can actually, Alice can move 2 steps, and Bob can move 5 steps. So in that case, in the first round, Alice can move here. Let's move a little bit closer to Bob. Let's move here. And Bob can stay here out of the range of the Alex can reach in next round, right? Because in the next round, Alice can at most move here, right? So in this case, Bob can stay here. And Alice can, in next round, Alex can move here or here, right? Let's say she moves here. Uh, at that time, Bob can just move here, still out of the range of the Alice move in next round, right? So Alice can never reach Bob. So Bob can win. So we output Bob. So we can assume that Bob and Alice all take their optimal moves, but eventually one of them will win, and we output the name of that winner. So how do we solve this problem? Um, so just a intuition, right? So Alice is going to chase Bob. So uh, if the distance between Alice and Bob's original point is less than Alice's dA, right? This is the number of distance can Alice move. So if distance between Alice and Bob is less than dA, less or equal than dA, then in the first round, Alice can just move straight forward to Bob's place and win the game, right? This is the easiest case we can think of, right? Um, how about others? Let's take a look. So, so winner equals 0 means Alice wins, right? So if the distance between Alice and Bob less or equal than dA, then Alice wins. That's the case we already described. And if 2 multiplied by dA bigger than the diameter of the graph, then Alice wins. Why is that? Because let's say this graph's diameter is 1, 2, 3, 4, 5, right? So if let's say if we change a number here, change Alice's dA into 3, then um, the first move of Alice, we can move it, move her to here, right? And uh, if Alice locates at this position, then she can move to any of the nodes in the next move, which means she can catch Bob in the next move, which means she wins, right? So if this condition holds, the Alice can just first move to the center of this graph, and then she can reach to any of the node in this graph, and she can win. So this is the second case. The third case is that if Alice, if 2 multiplied by dA is bigger or equal than dB, uh, that means, let's say, um, uh, let's say here we have we have dB equals to 4, right? In this case, Alice can just move one in each round. Alice can just move one step to the Bob's subtree, right? If she knows Bob is in this subtree, she can just move one step further. And because this condition holds, let's say Alice moves here. Even though Alice can only move 2 steps, um, Bob cannot skip uh, Alice and uh, move to another direction, right? For example, Bob cannot move here to here, right? Because 2 multiply dA is bigger than dB, right? So Alice can always move toward Bob. And in each round, Alice is one step closer than Bob. And because there are infinite number of rounds they can have, so eventually Alice will track down Bob, right? And Alice wins. So that's 3 um, win condition for Alice. And that's all the win condition for Alice. If all these conditions don't hold, Bob wins, right? Because Bob can always jump back and forth, and always outside of Alice's reach. So to solve this problem, we need to calculate the diameter of the graph and also calculate the distance between Alice and Bob as original points. So for each of the number, we are going to run a deep first search to calculate that number, right? So let's take a look at the code here. So we're going to read the number of test cases, and we're going to read those numbers, the number of nodes in the graph, Alice's original location, Bob's original location, the distance she can move, and the distance Bob can move. And read the graph, right? And let's initiate the diameter here. So, and the distance between Alice and Bob, and calculate the distance, calculate the diameter. And then we apply all those win conditions and see who wins, right? And the key part is how to calculate the distance between Alice and Bob. So we are going to calculate it with deep first search, right? So this pair is going to store the location of the Alice and Bob, right? The first number is Alice and the second number is Bob. So if all of them equals to -1, that means we haven't encountered these 2 original points yet. And if current node is equal to Alice's original position, we make the first number 0, right? And each time we go one step further into the deep first search. We are going to increase the dips of the Alice's original position by 1, right? And eventually, if we find a node that has both of the Alice and Bob's location, I mean, both of their dips, we're going to sum it up and return it as the distance. What does that mean? So we can draw a simple graph here. Right? Let's say Alice is here and Bob is here, right? So we are going to run the deep first search. And let's say this is our route and we go this way. We haven't found Bob and Alice and go this way. Haven't found anyone and go this way. Oh yeah, we found Alice here. So the initial depth is 0, right? And we backtrack here. So now the Alice's depth is 1, right? And we backtrack and we deep first search. Oh, we find Bob here. So Bob's initial depth is 0 and Bob's backtrack. Now Bob's depth is 1 and Alice's depth is 2. So this guy has both of their depths. So we add them together as the distance, which is 2 plus 1 equals to 3. So the distance is 3, right? So that's how we calculate the distance between two nodes, right? And what about the diameter here is quite similar. So, so we are going to deep first the tree again. And each time we are going to save the dips of the children of that node, right? So the C here is going to save um, each of the subtree dips for this node, right? And the return of this function is the dips of this node, right? And we save the children's dips here, and if the number of children equals to 0, then that means this is the leaf node. So we just update the diameter with 1, right? So the diameter is the longest path we can find in this tree, right? And here is the depth of our current node. So so this is the maximal depth of its children, and we are going to plus 1 into that number, and that's depth of the current subtree. And we are going to update the diameter with that depth. And if the number of children is bigger than 1, then we are going to use the biggest, use the maximal dips and the second maximal dips and add them together. And that number is the maximal diameter for that node, right? And we are going to use that number to update the diameter. So for example, if we have a tree like this, so we are going to start from the root and calculate the depth of this root. So so we first traverse into the calculate the depth of this subtree and depth of this subtree, right? The depth of this subtree is 0, 0. And when we backtrack, the depth of this subtree is 1 and 1, right? And this is the biggest and this is the second biggest. And we add them together to get 2. So the biggest diameter we can have for this node is 2 from here to here, right? 2 as a distance. And the depth of this node is 1, and we backtrack. The depth of this subtree is 2 now. And also, the depth of this node is 0, this node is 1, this node is 2. Here we get a 3, right? And what is the diameter for this node is 3 plus 2 equals 5. So the longest path is 1, 2, 3, 4, 5, right? This is the diameter. So that's how we calculate the diameter here. So that's it. We calculate the diameter, we calculate the distance, and we solve the problem. So that's it. That's for today's problem. Thank you for watching. Bye.